Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about polynomial interpolations. Okay, so yeah, let's just hop right into it. So let's say we're given a discrete data, and this data is in the form of vectors. Specifically, here we're given column vectors. So let's say we have some x vector, x1, x2, all the way to xn, and as well as a y vector. So this goes from y1, y2, all the way to yn. And so yeah, we're given these data where we know there exists a function f. So we're going to assume that there is a possibility. So there exists some function f such that if we were to plug in a certain x value, well, we would get its y value, right? So we would get its y value. But the problem here is that we don't know f explicitly, right? We can't find a certain function given these amounts of data, our x values and y values. And so we're going to find an approximation of f, right? And one way to do it is through interpolation. So that's this idea of interpolation. Based on some discrete data, we're going to find a function where if we plug in these x values, we're going to get the corresponding y values. And so that's what we're going to do. And so, okay, let me just give the instructions. So we're going to approximate this function, right? Um, we're going to use interpolation. Now I'll get to how exactly interpolation works in a bit. We're going to approximate this using interpolation um, such that this function is approximately some other function, and we're going to get that yj value. And so here, what's happening here in this function, specifically this, is that g interpolates the data. Okay, so first let's build a basis, right? Let's build a basis of this function. And the easiest one is what we call a Lagrange polynomial. So let me just Google that up a bit. Actually, let me Google interpolation of functions. Meaning, what does interpolation actually mean? Interpolation is the process of estimating an unknown value between two known values. So we know x and y. We pass some data there to that function, and then it will be used to estimate values at points where the original data was not provided. That seems cool. Okay, so first let's build a basis, right? We're gonna use Lagrange polynomials. let's do this. So what are Lagrange polynomials? So I haven't talked about that. Pretty sure it's a pass. Okay. So this is a numerical analysis, but the Lagrange interpolating polynomial is the unique polynomial of lowest degree that interpolates. So basically, it's used to interpolate data. That's basically what it is. So it's meant for me not to know, actually. I haven't taken a numerical analysis class. Okay, let's just go through it. So what's a Lagrange polynomial? Well, it's something used to interpolate, obviously. Let's just do it. So we have our Lagrange polynomial uh, at j. Well, we plug in some x value. And this is basically, well, this is how you write it. It's that symbol. Looks like a pi, actually. It's kind of funny. I starts at 1, but I can never be j. Okay, that's interesting. And x, we're going to subtract that to some xi. And then here we get our Lagrange x, some k value. Is that k? Oh, yeah. This is equal to 0. For k not equal to j, right? Why should it not be equal to j? Well, if we know xj, that's already a known value. But here we're trying to build, we're trying to estimate unknown values based on known values. So that's why we don't make it a j. Okay, so let me continue. So it's gonna be over. Okay, we do this. This is n xj minus xi. And then this is I equals 1. And then this is I, again, not being equal to j. Well, here, my Lagrange as x sub j should be equal to 1, right? And so we see that L sub j, when we plug in our known point, or no, not our known point, my bad. Sub I, you plug in some ith value. It's either going to be two things. It's going to be a 1 or a 0, right? It's going to be a 1 if my j is exactly my I. So if I find the value itself, it's going to be 0 if my j is not I. And then from there, let me continue. My y value times my Lagrange at x I. Well, now this is going to be equal to yj as j is equal to I, and 0 is not, j is not equal to I. So I'm going to get an output of yj. So the idea is to use this Lagrange polynomial to get 1. And then once we get 1, we multiply it by yj to get yj. Right? So that's the idea. Okay. Now let me. So since this holds, we basically have, okay, let me not do a summation yet. We have y, let's use k, why not? K starts at 1, all the way going to n. So yk Lagrange k xj is going to just be equal to yj. So the idea is I use this Lagrange function, Lagrange polynomial function, and then from there I do a summation until I reach some n, and then I'm going to get that value yj, right? Okay. And so now we can define this. So if, for convenience purposes, let's define this as a function of g. Let me make it a function of g, this summation from my yk Lagrange k xj, or not even xj, just x in general, right? Because I'm just plugging in that x value. Well, then I say that that function with the Lagrange and the summation, if I plug in my xj, I'll get my yj, right? So here now we're building up on something. Now we're kind of creating a function that will help us lead to an output yj. And so what am I saying here? I'm saying my g of x is a polynomial approximation. So this is just, at the end of the day, there's no such thing as perfect numbers. And so, well, when involved with real data. And so here we just basically use approximations. And this is a degree of n minus 1, right? Why is it n minus 1? Well, if I look at my Lagrange polynomial, then this goes from, let's say I starts at 1, but I should not be equal to j, x minus x1, xi, I mean. Well, this multiplies n1 n minus 1 x terms. So it multiplies that many terms, n minus 1 x terms, right? Yeah, okay. So there exists multiple basis functions. Yeah, there are a lot of basis functions to interpolate or to make function approximations. One of these was the Lagrange, which we just did. But yeah, okay, there's just a lot of wording here. But basically, okay, so there exists a lot of basis functions, right? To create function approximations. One of them could be, I don't know, this rho, mostly used for density, but I'm going to use this anyway. This rho, and sometimes these have the form, let's say, g of x, right? G of x is my polynomial approximation. It's just going to be some summation going all the way to j, cj. I'm going to say cj is some constant, and then my rho. And what I'm saying is that cj is not necessarily data points. Cj, not necessarily data points yj, right? And we use different basis functions, raw x, for different characteristics, right? So for instance, where j is equal to 0 all the way to n minus 1 and raw is equal to 0, well, our raw jx is x naught. And if we take its derivative, oh no, x to the power of j, we take its derivative. Let me actually read this real quick. We take its derivative, we replace it with some function, and then we find something else. Now my g prime of x is a function that is also decomposed into rho j. And moreover, if we know Cj, we can find the coefficients of C prime j, namely Cj plus 1, j plus 1, through matrix vector product. Okay, let me write all of these out before because usually when I write it out, it's okay. I'm just gonna write it out. I don't fully understand it, but I'm gonna write it out because I might get it along the way. So what we're saying is, there are a lot, or there are multiple basis functions. And we're going to say rho sub j of x to create function approximations, right? So there are tons of basic functions to create these approximations. And these usually have the form. So these have the form. So g of x is my function approximation. I do a summation here. And I do j, cj, rho j of x. And well, this is just going to be what? Or what's my cj doing here? My cj is not data points yj. So it's not necessarily that. And so we can use different basis functions, rho of jx, rho sub jx, for different characteristics, right? So let me write that out. So we can use our rho of jx for different characteristics. So it's based on the context, right? So let's do an example. So for example, we have rho of jx is x naught, right? Or x to the power of, oh my bad, not x naught, x to the jth. And we're going to say j goes from 0 all the way to n minus 1, right? Goes all the way to n minus 1. And so from there, we have that my rho, when I take its derivative, so this is a calculus thing, then I just take the derivative of x to the j, so I get j x j minus 1. And then from there, I get j rho j minus 1 x. right? So here my xj minus 1, I use my function again. And then from there, so what do I notice? I notice that when I take the derivative of my function approximation, well, this is going to be n minus 1. This is going to be j equals 0. And then this is going to be cj rho j of x, then the derivative of that thing. And what is this going to be? Well, I can keep on going. This is a summation of cj j, then rho of j minus 1 of x. And this goes from j equals 0 to n minus 1. And then again, I can do it again. Now it goes from n minus 2, right? This is from j equals 0. And I get cj plus 1. Then I get j plus 1. And then I get rho j of my x. So I keep taking the derivative again and again, right? And then from there, well, I get to... So at the end of the day, well, what do we realize? We realize that g prime of x is a function that is also decomposed. So again, when we decompose something, it's usually good because we increase efficiency or we make it faster into, not p, into rho sub j. So at the end of the day, it's going to continue going up until we reach rho sub j, right? And moreover, if we know c sub j, right? So let's say we know exactly what c sub j is. If we know what that is, of my function approximation g of x, we can find coefficients of g prime of x, right? So we can find coefficients of g of x. And so that's going to be, or not g of x, g prime of x. Well, that's just going to be c sub j plus 1, and then c. Or no, not c. J plus 1, right? And from there, we can easily compute the coefficients of g prime of x through matrix vector product. So we can do this. Oops. Coefficients of g prime of x through MATLAB or matrix vector multiplication. And so let's do that actually. And so we're going to let the coefficients of g prime of x be denoted by, let's do d. Why not? Right? So we're going to say, let coefficients of g prime of x And we're going to set that to be denoted by that D symbol. And so we're gonna say that my D symbol is gonna be a tons of numbers, right? So it's gonna be 0, 1, 2, 3, 4, all the way to n-1, and then the rest are gonna be zeros, right? So these are all just gonna be zeros. Okay, let me organize it real quick. Okay. We have 0. Yeah, so these are all just pretty much zeros, right? We only have these. So let me highlight. This is all that we have. Okay. And so from there, the other benefits are that Cj is easier to compute depending on the raw j. And so let me see. However, at the end of the day, the function g that interpolates for x and y is unique. So it's always going to be unique. No matter which raw j you use, the corresponding coefficient Cj will make it so that you can simplify the summation of Cj raw j to the same function. And so we are not only limited to polynomial interpolation, we can also split the domain into multiple parts and create a polynomial on that segment, right? And so maybe an example. So we're not only limited to polynomial interpolation, right? So we can say, for example, let's do, or if we're given a scenario, let's say my x sub 1 is less than x sub 2, which is less than or all the way to x sub n. So I'm going to assume my x sub n is the biggest. Well, now we're going to define a new function. Let's use this Greek thing. It's called psi. This is equal to, let's say, x minus xj all over xj plus 1 minus xj. And this is equal to, well, yj plus 1. And we're going to add to x minus xj plus 1. So what do we notice here? Xj minus xj plus 1. Yj. Right? So what do we notice? It looks like a linear something. Not super sure. Then our interpolation or our function approximation, right, is going to be some piecewise. So if we say 1, so let's say that that's our function, right? That psi, let's say it's psi sub 1. Well, this is going to be specifically for x sub 1 inclusive, or we're going to find an x in between x sub 1 and x sub 2. So we can do that. For psi 2, well, we're going to find from x sub 2 to x sub 3. exclusive. And then we continue. So when we do all the way to n minus 1, well, that's going to be xn minus 1, x, xn, right? And this interpolates f, right? So this interpolates f for the sole reason that our function approximation g gives us some y value, right? And so interpolation can make a continuous function out of data points. And we can now predict what happens in between these data points. However, we don't know if this is truly going to be the actual function. And we can only go closer and closer by observing more and more points. And so given these points, how do we practically find the coefficients? It's also another thing. So how do we find the coefficients? So given more points, how do we find, let's say, coefficients? We're gonna do c sub j in this case of my g of x. So my function approximation, this is a summation of my cj rho j x, where it will give me some output, right? And so, okay, let me try. Okay, here's what I'm gonna try. Let's say my rho is going to give me an output of the actual x value, such that my function approximation then is some summation from j starting at 0 all the way to some n minus 1, n minus 1. And this is cj x to the jth power. What if we do that, right? And so since, well, my g of x sub j, or x sub I, my bad, my x sub I is just equal to y sub I, for given I is equal to 1 all the way to n. Well, we have n equations and n variables cj. And that makes sense, right? Because we have n unknown variables, so we need n equations. And so we have, well, we have polynomials, right? All the way to some n. Wait, that's a thing. Okay, let me just write out the system. So here's our n equations. It's basically a general system. So let me put the, okay. So it's basically this. We have C naught, right? That constant. C1 x1, C2 x sub 1 squared, right? Then we're going to continue all the way until we reach C sub n minus 1, all the way to x n, which is equal to y1, right? We do it again. C sub, assuming this is 1 still, x2, C sub 2, x2 squared, and then this goes all the way to C sub n minus 1, x2, and y2. And then we continue. Let's find some x value, or some k value, my bad. Some k value. So this is C, still C1. Still C1. C1. Now this is my k value. This is my k value. This is C n minus 1, x k, n, y, k. And then we go do it all the way to n, right? Let me quickly do this. X n squared, n minus 1, x n n, y n, right? And so we can solve this system using matrices. So let's actually define a matrix that will help us solve this. So that's what we've been doing so far. Given some linear system, well, we want to translate them into matrices so that the computer can use it. So we can solve this using matrices, specifically one that I would introduce, the van der Waals matrix. Which I'll just denote as a V. So let me do that. So here I get 1 x1 squared all the way to x1 n minus 1. And then I do that again and again and again. X2 then I go all the way to n. Right? And then from there, well, we can just find C. The coefficient C. How do we do it? Well, we solve our matrix B. This van der Waals matrix, C is Y. We have our Y. We have our van der Waals matrix. Then we solve it using decomposition, using iterative schemes, gradient descent. And yeah, that's how we're able to do it. Okay, that's it for this video. I hope you guys enjoyed. I hope you guys learned a lot, and I'll see you in the next one.